In the previous video, we talked about continuity, and in those problems, they were always phrased as, is this function continuous at this value? Is this function continuous at this value? It was always sort of like, here's the value to be thinking about, check and see if it's continuous there. For these problems, I'm not going to be asking that specifically. I'm just going to say, here's a whole function, tell me if it's discontinuous anywhere. And on the surface, that may sound frightening, because that means, oh no, I need to check every single x value. And it turns out there are lots of them, like, infinitely many x values. And so that would probably take a little while. So we're going to need sort of a strategy for how we're going to do that. So I'll get into that strategy, but before we get there, this title even implies that there are multiple types of discontinuities, because classifying means separating into different categories what kind of discontinuity you're working with. So the first thing I need to do is I need to show you what those discontinuities are. So here they are. The two types of discontinuity you need to know about are called a removable discontinuity and a non-removable discontinuity. And the entire difference, the entire thing boils down to limits. Right? In some sense, a lot of this chapter being about limits has been leading up to this idea of continuity. Right? So let's just get to it. A function has a removable discontinuity at a particular x value if the limit exists but is not equal to f of c. It may help you to know that a removable discontinuity is the same thing as a hole in a graph. And if you think about what a hole in a graph looks like if you imagine that you have a graph of some function and it has a hole in it, like if you've got something like this going on, in that instance you can see from the picture, I hope you can see this, I hope you can see the limit exists, but f of c would mean that that value, whatever that thing is, it's saying, sure, that's what the limit is, but whatever f of c is, wherever the point is, it's not that. Right? So removable discontinuity means the limit exists, but it's not equal to the value of the function. Either the function is undefined, or the value of the function is simply different. Okay, so that's what a removable discontinuity is. By the way, it's called a removable discontinuity because you could remove the discontinuity. How could you remove it? Well, if that point wasn't there, like if it was up here, then yay, it's not discontinuous anymore. I filled the hole. Woo! Right on. Let's move on and talk about non-removable. A function has a non-removable discontinuity. By the way, a non-removable discontinuity means that it has a jump or an asymptote on its graph. It's non-removable if the limit just doesn't exist. And by the way, I just realized there's a typo there. That f of c should have been f of x. Okay? So, function has a non-removable discontinuity, means it has a jump or an asymptote, if the limit doesn't exist. And this makes sense too. If you think about a graph for which the limit doesn't exist, there are two possibilities. Either you've got something like this, which I would call a jump, or you've got something like this. Right? In both of those cases, the limit doesn't exist. Right? In both these cases, it doesn't exist. Now, you may wonder, oh, well, couldn't you remove the discontinuity by, just connecting them? Well, here's where it's actually kind of fun. If I tried to connect these two things together and be like, yay, it's continuous now, why is that a problem? Pause the video and think about the language of functions and think about why that's not possible. The reason is the vertical line test. This would hideously fail the vertical line test right there. There are billions of points right here where that would fail. Same deal here. If you were just yay, I'm going to just connect the two sides, woohoo! No, right? You fail the vertical line test. You cannot remove these discontinuities because it's not a single point that's missing. It's many, many, many points that are missing, and that's why it's called non-removable. Alright, so the next thing we get into is, so how do we figure out, how do we classify these discontinuities? How do we do it, right? Well, step one is you have to narrow down what you're looking at. We can't possibly check every single value for continuity, so we're only going to check the usual suspects, right? So we want to find all possible input values that could cause discontinuities. The two major causes of discontinuities are division by zero and the jumps in piecewise functions. In fact, I'm going to go so far as to say those are the two causes. If there's anything else, it's sufficiently weird that we probably don't need to know about it, right? So, first thing you do is you make a list of all the places where division by zero happens and all the places where piecewise jumps happen, right? Step two, for each input value, you find out if the limit exists. Okay, so for each of those values, take the limit, right? And then we kind of get into two different categories here. So step 3, if the limit doesn't exist, automatically non-removable discontinuity, done. Like, simple as that. As soon as you see that the limit doesn't exist, and that includes infinite limits, right? So if the two sides are both going up towards positive infinity, nobody cares. It's not like they meet up there. They're just getting close, okay? So if the limit doesn't exist, non-removable, done. If the limit does exist, we have a little bit more work to do, right? If the value of the function is equal to that limit, in other words, when you actually plug in c, like at this point we're doing a test for continuity, right? If when you actually plug in c it matches the limit, it's actually not even discontinuous, it's just continuous, right? Because that means that the limit existed, and yay, the function was there too, woo, we all win, right? But if the value of the function is not the same as the limit, or doesn't exist, then the function has a removable discontinuity, because it means the two sides of the function came together, but either the function was undefined, or it was defined somewhere else, and in either case there's a hole and it's a removable discontinuity. Alright, so I have a few examples for us to look at, and here's one of them, right? Find and classify any discontinuities in this function. So step 1 was supposed to be us determining our usual suspects, right? So what are the problem spots going to be? We said division by 0 and piecewise jumps. This is not a piecewise function, so all I'm really looking for here is division by 0. So I'm looking at, effectively how do I factor the denominator there, right? If I factor that as 2x and x, so let's see here, we'll have 2x minus 1 and x plus 3, it looks like. And so if we solve these things, we're going to end up with x being 1/2 and x being negative 3. These are my potential discontinuities. Okay, so then step 2, my next step is where I take limits to try and narrow this down, right? So I will take the limit as x approaches 1/2 of my function, which is, and at this point, like, you may even want to start moving things around. Like, for instance, I can tell the denominator is going to have a 2x minus 1, so it might help to take this 1 minus 2x and rewrite it. Like, make that negative 2x minus 1, because we know what's going to happen with that. We can tell that that's going to cancel with what's in the denominator, right? So, in fact, these things will cancel here. Now, when I plug in 1/2, I'm going to end up with negative 1 over 3.5, which is 7/2. So that means my limit is going to be negative 2/7, right? So that means my limit existed, which means it's not non-removable. But let's sort of move on and do the other part of this one. I also need to do the limit as x approaches negative 3 of the same thing, of my negative 2x minus 1 over 2x minus 1 times x plus 3. In this case, I'm going to end up with, something looks like positive 7 over 0. As soon as we see that this limit didn't exist, we know that there's a non-removable discontinuity at x equals negative 3. Like that's set, that's done. I don't even need to do any more work with negative 3. We've already figured out what happened, right? On the other side, there's a little bit more work to do. We noticed that this limit here existed, right? It was negative 2/7. So now I need to look at what actually is, and I suppose this is sort of like step 4. I need to figure out what is g of 1/2. What happens when I actually attempt to plug in 1/2? And what you'll notice here is that when I attempt to plug in 1/2, I get 0 over 0, which is undefined. So what does it mean if the limit exists, but the value of the function is undefined? Right? Well, if you remember from our steps, what this means is that there's a removable discontinuity. And at that point, we're effectively done with the problem. We've classified the two discontinuities. There's a removable discontinuity, which means there's a hole. There's a hole at 1/2 comma negative 2/7. And there's this non-removable discontinuity, a vertical asymptote, basically, at x equals negative 3. Right? So that is the classification of the discontinuities for this problem. There's my next example. Again, find and classify any discontinuities in this function. So, pause the video, work through this on your own. Step 1, again, is that we sort of go through and we figure out what are the problem spots going to be. So the denominator, I have x times x plus 2 equal to 0. So x equals 0 is going to be one of them, x equals negative 2 is going to be the other one of them, the function has division by 0, but is not piecewise, so that's all I really need to worry about. The second step is where we actually work out what the limits are. So I'll take the limit as x approaches 0 of the sine of x plus 2 over x times x plus 2. When I attempt to take that limit, I'm going to end up with, like when I attempt to evaluate for 0, I'm going to end up with the sine of 2 over 0. And so that means that this limit does not exist. So immediately, what does that tell us about discontinuities? Hopefully you recognize that means that there's a non-removable discontinuity at x equals 0. Right? The other part of step 2 is where I now do the limit as x approaches negative 2 of the sine of x plus 2 over x times x plus 2. In this case, when I attempt to evaluate for negative 2, I end up with, basically 0 over 0, which means try harder. And hopefully you recognize here, this is one of those special limits. I have the sine of x plus 2 over x plus 2. In fact, if I were to manipulate this just a little bit, if I were to put that x out front, like a 1 over x times the sine of x plus 2 over x plus 2, I hope everybody recognizes what you could do with this limit right here. Right? I hope you all recognize that that limit turns into 1. Why does it turn into 1? It turns into 1 because these things are the same as one another, and as x approaches negative 2, they both turn into 0. When that happens, that's a special limit, it turns into 1. So now all I really have left is this part of the limit, right? And that limit, I can just evaluate for negative 2 and find out this limit is negative 1/2, right? So in this case, the limit existed. Now, again, I'm sort of going on to step 4, where I'm looking at, okay, in step 4, what is the value at negative 2? Like, what happens when I actually attempt to plug in negative 2, like for real? And when I attempt to do that, I end up finding that it's the sine of 0 over 0, which is undefined. So what does that mean in terms of continuity? Hopefully you recognize that means that it's a removable discontinuity. The limit existed, the value of the function did not match, and so because of that, it is a removable discontinuity at x equals negative 2. And again, we've effectively reached the end of the problem. We have found and classified all discontinuities, and that's what we were asked to do in the problem. This problem is something of a favorite of mine. It also has this tendency to show up on AP exams. And so, it's a good thing for us to know. Dealing with piecewise functions is a big one, right? So they want you to find the values of a and b so that this function is continuous, right? Well, and if you're feeling up to it, pause the video, try this one on your own. I feel like you guys probably have the tools that you need for this, but you're going to need to think about it. So if you need some leading advice, here it is. What does it mean if this function is continuous? The function is continuous means that, like, every problem spot ends up not being a problem spot. Right? Well, what are the problem spots here? Where are the potential discontinuities? The potential discontinuities, there's no division by 0, it's the piecewise jumps. It's at x equals negative 1, and it's at x equals 2. Those are the two spots where you might have trouble. Right? So in order to make this function continuous, I need to make sure that my function is continuous at those values. And this is where I'm going to ask everybody to pause the video if you haven't already tried it on your own. What does it mean if the function is continuous there? Very specifically, it means the limit exists and the value of the function is the same. So my question to you is, how are you going to guarantee that the limit as x approaches negative 1 of h of x exists? And also, how are you going to guarantee that the limit as x approaches 2 of h of x exists? And if you haven't paused the video and tried this on your own yet, I really feel like you should here. I think you should pause it and try and work out what would this mean. Well, if the limit as x approaches negative 1 of h of x exists, it means the limit from the left and from the right at negative 1 have to be equal, right? So how do I approach negative 1 from the left? Well, from the left, it would mean I would use this function. So I will evaluate this for negative 1. When I evaluate that for negative 1, I end up with 1 minus a plus b. That will have to be equal to the limit from the right. Well, how do I approach negative 1 from the right? Well, from the right of negative 1, I'm going to use this one. So I'll evaluate this expression for negative 1. So that's going to give me negative 1 plus 2b, not equals, plus 1. Right? So when all is said and done here, I end up with 1 minus a plus b equals 2b. And if I move stuff around a little bit more, let's see here, I'll end up with, I could even do 1 minus a equals b. And some people are like, oh no, I have two variables. How do I solve for a and b? This is so common. If you ever have an expression that's two variables, it probably means there's a way to get another equation. And if you can get two equations, you can use substitution or elimination. So let's keep moving through this. On this one on the right, to make sure that the limit as x approaches 2 exists, I'm going to approach from the left and from the right. I'm going to evaluate this expression for 2 and this expression for 2 and make sure they're equal to one another. So this is going to give me 2 plus 2b plus 1 equals 6 minus a. So again, I can sort of move stuff around here. I could end up with, let's see, this is 2b plus 3 equals 6 minus a. So I could, to be honest, at this point I could even do substitution. I could just take this 1 minus a and substitute it in over here for b, right? I would have 2 times 1 minus a plus 3 equals 6 minus a. So that's 2 minus 2a plus 3 equals 6 minus a. And at this point I'm just sort of doing basic algebra here, right? This is negative 2a plus 5 equals 6 minus a. I'll move the 6 over and the negative 2a over. That'll give me negative 1 equals a. Cool, so we found that a was negative 1. If I take that and substitute it back into the other, I'll end up with 2 equals b. Those are the values of the function that cause this function to be continuous everywhere. Okay. When I say this is a favorite problem of mine, it means there's a really good chance it's going to show up on our exam whenever that happens, so, interpret that how you will. So, hope that made sense. I know this is a long video, but hopefully you stayed strong.